Last few classes, we've been working on least squares fitting. We started with linear least squares fitting. We could solve that problem analytically. We worked towards nonlinear least squares fitting, where we use iterative methods for the least squares fitting. We talked about data space and model space as helpful visualizations. We talked about the residuals vector. We talked about the chi-squared as a length squared of the residuals vector. And we talked about uncertainties on the best fit parameters. We talked about correlations between the best fit parameters. And we looked at examples drawn from astronomy, expansion of the universe, and examples from particle physics, fundamental elementary particles. Today's class, I want to move on to the numerical solutions of partial differential equations. We'll talk about the numerical solutions of partial differential equations over the next few classes, either 3 or 4 classes, I can't quite remember. We've already talked, of course, about the numerical solution of ordinary differential equations. We spent a few classes on that. So our work on partial differential equations, solving them numerically, will be partly built on our work on ordinary differential equations and solving them numerically. There's some important similarities and some important differences between numerically solving PDEs versus ODEs. I'll mention that on the next slide. We're going to look at applications over the next few classes. We'll look at applications in electrostatics, that's this class. We'll look at applications in thermodynamics next class. We'll look at applications in mechanics, fluid mechanics, next week, I think. Okay. This slide was meant to summarize ways in which ODEs and solving them numerically and PDEs and solving them numerically are similar, and ways in which the two are different. So on this slide, they're similar in the sense that for the ODEs upstairs here, I consider the same items, so the same items come up. For the PDEs, I've listed the same items are currently now. The comments about them are different in two cases. So if I was to compare solving numerically ordinary differential equations and partial differential equations, first thing about ordinary differential equations is you're working with a single variable, a single independent variable. So we were often working with time as the single independent variable when we were solving the ordinary differential equations associated with a falling body, or the ordinary differential equations associated with a pendulum motion. So one independent variable. When we specified the initial conditions for the falling body or for the pendulum's motion, we specified those initial conditions at a point or at a moment in time. We only need to specify the initial conditions at one point, one moment in time. That's the key thing with the when we solve for the trajectory of the falling body or the trajectory of the pendulum, we were solving for the trajectory of a single variable. And we were solving it with the aid of the Taylor expansion to different orders that gave us what we named the Euler method, or what we called the Runge-Kutta method. So we were working with a single variable and simply applying Taylor expansion. So very unified approach. The stability of our solutions to the falling body or to the pendulum's motion was really determined by, really governed by the time steps that we were taking, or the steps in a single variable that we were taking. So if we made those single steps smaller steps, we would increase the stability and precision. We made them larger steps. We would decrease the stability and precision. And we could estimate the stability and precision just by considering the Taylor expansion. What about partial differential equations? So big difference with partial differential equations, now you've got multiple independent variables. So two or more independent variables. So you might have a problem where you're interested in the electrostatic potential in some region of a two-dimensional space. That's a partial differential equation in two spatial variables, say x and y. It could be in three dimensions. It could be in x, y, and z, or it could be in three dimensions where it's r, theta, and phi. So we've got multiple dependent variables. It could be a diffusion equation, that's a partial differential equation that depends on space and time variables. So it could be a partial differential equation in a space coordinate and a time coordinate. Or it could be in x, y, and t, or x, y, z, and t. So again, multiple independent variables, big difference. Now, the initial conditions are not specified by, you know, the location and velocity of a falling body at a certain point in time, or the location and velocity of a pendulum at a certain point in time, but rather the initial conditions or boundary conditions are specified often over some surface, around some surface, or after some surface surrounding some volume. We've got, instead of initial conditions, boundary conditions at a point, you've got initial conditions, boundary conditions over a line bounding a two-dimensional surface, or over a surface bounding a three-dimensional volume, or even more complicated boundary conditions when you've got time and space in the partial differential. So that's a big difference. Unlike the case of ordinary differential equations, where there's really one unified approach to solving them numerically. The unified approach is to take the Taylor expansion and, using the Taylor expansion, take steps through that single variable. Maybe you use the Taylor expansion to second order or fourth order, but you're basically taking a Taylor expansion and stepping in a single variable. What you discover in partial differential equations is there's not really a unified approach to solving partial differential equations. There's much more of a kind of piecewise approach to solving partial differential equations. For some types of partial differential equations, it might be that one approach is good. For another type of partial differential equations, it might be some other approach. So we use piecewise different approaches to partial differential equations. So, and we're going to try and get some experience of the different approaches over the next few slides. The stability of the solutions to the partial differential equations is also more complex, more complicated, less unified. We're now not stepping in a single variable, and we've got a single step size, say delta t, in which we can evaluate stability. Now we're stepping in multiple variables, maybe it's x and y to solve a Laplace equation, maybe it's space and time to solve a diffusion equation. And it becomes more complicated with different steps in different dimensions in space and time to evaluate, estimate, precision, and stability. So that's a difference. We'll be solving a broader class of problems. As I say, in ordinary differential equations, we kind of focused on falling bodies, projectile motion, pendulum motion, or oscillatory motion. And we're going to take a broad sweep across electrostatics with Laplace's equation, thermodynamics with the diffusion equation, and mechanics with a wave equation. Another important equation that you partial different equation that is, of course, Schrodinger equation. So that's another example. Okay, today's class we're going to focus on Laplace's equation from electrostatic. It's typically the first problem that you would solve numerically as an example of numerically solving partial differential equation. Kind of a classic example of partial differential equations. It's relatively straightforward because although we're going to look at Laplace's equation in 2 dimensions, although it's got 2 independent variables, say x and y, they're on kind of equal footing. It's not space and time, it's just 2 dimensions. Okay, I got a few slides here about Laplace's equation and Poisson's equation, and about methods for solving Laplace's equation and Poisson's equation. Sort of about how we the methods that we go about analytically solving them, and then to introduce the method that we use for numerically solving them. And a very important characteristic, property of solutions of Poisson's equations. So just to get us going, in electrostatics, if we drop into electrostatics now for a little while, for one part, in electrostatics, you might think of 2 classes of problems. In one class of problems, you are told a distribution of charge. It might be an arrangement of point charges, or it might be a smooth distribution of charge. And you're asked to you want to figure out the electric potential, electrical field. So that's one class of problem where you know the charge arrangement and you want the electrical field or the electrical potential. Another class of problem is where you want to calculate again the electrical field and the electrical potential in some region of space, but you're not specified the charges, the arrangement of charges or the distribution of charge. You specify the electrical potential on the boundaries of that space. Here's a picture of that, right? We want the potential inside this rectangular region. The potential is specified on the outside of this region. There could even be boundaries interior as well as external boundaries. So this is a second class of problem. And this is solved by solving Laplace's equation if you don't have charges in your region of interest, or Poisson's equation, you do have charges in your region of interest. For the illustration today, we'll just stick with that. Okay, so Laplace's equation just falls out of the field equation that describe the working properties of the electrical field. And Laplace's equation is just a partial differential equation for the electrostatic potential in electrostatic. So as it falls out of the field equations, I wrote up on the slide the 2 field equations for the electrostatic field for the divergence over here. The other field equation is that the electrical field is a curless electrical field, or equivalently, you can say that the electrical field can be represented by electrostatic potential. So those are like the kind of founding fathers or whatever of the electrostatic electrical interaction that specify the field or are related to the specification of the field. And if we just put them together, plug the expression on the right, the electrical field, gradient of the potential, into the electrical field in the divergence of the electrical field being determined by the charge density, then we get this equation here. This is Poisson's equation for the electrostatic potential. It is variant where you're in a region of space where there's no charge density. zero, then this is Laplace's equation for the electrostatic potential. So these two equations are second order partial differential equations. The second order linear partial differential equations, one of them's homogeneous and one of them's inhomogeneous, which just means that either the right-hand side of the equations are zero or non-zero. They're linear in the sense that they're linear in the electrostatic potential, which is the function that we want to solve. They're morally variable in the sense that they depend on the spatial coordinates. So the differentials are with respect, say, to x and y and z, or with respect to the spherical or the cylindrical coordinates. So that's Poisson's or Laplace's equation. You've met these before, sure, undoubtedly. An important point about the solution to Laplace's or Poisson's equation, an important property of the solution to Laplace's or Poisson's equation, is that supposing you want to find the solution in some region of space, you want to find the solution for the potential in this region of space represented by this sort of gray block. Well, that's the interesting volume in gray, and it's surrounded by some bounding surface, this black line here, on which we specify the boundary conditions. So this is the type of problem that we're going to address. This is the type of problem that there are methods to solve analytically, and there are methods to solve it numerically. The uniqueness theorem says that it's somehow you come up with a solution to this problem for the potential in a region of interest that matches the boundary conditions on that potential in that region of interest. So matches the boundary conditions, I call them phi naught on the potential and E naught on the electrical field. If the solution matches those boundary conditions, then it is the single unique solution to the problem. So what that means from a practical point of view, solving problem point of view, is no matter how you can come up with, dream, or guess a solution to your problem, if it does match your boundary conditions to the problem, then it is the single unique solution. You have found the solution to the problem. So that's a useful thing. That comes up in a couple of methods for solving Poisson's equation or Laplace's equation. Here I got Poisson's equation. Next slide I got Laplace's equation. This is sort of a classic example of using the uniqueness theorem. Supposing we had an arrangement where we have a conducting plate and a point charge. And here in the generator, the conducting plate is standing vertically and it's grounded. So it's at potential 0 volts. And then here is a point charge in the neighborhood of the conducting plate, placed to the right of the conducting plate at some distance A from the conducting. So the question is, what is the electrostatic potential in this region of space that's towards the right of the conducting plate in which this real charge exists, given that we've got this real charge of charge Q, and it's to the right, a distance A from a conducting plate, which acts as a boundary condition where the potential is 0 everywhere. So the method of images way of solving this problem is to say, well, look, I want this potential for this situation over here on the right-hand side. But I'm going to guess that it resembles the potential for a simpler arrangement. a symmetric arrangement of one positive charge and one negative charge on either side of this vertical line. So I just make a guess that, well, this potential on the right-hand side is the same as the potential that's made by this two-charge arrangement of equal and opposite charges situated at equal and opposite distances from the vertical line. That's an electrical dipole that is a very familiar charge distribution. So they make an electrical field that looks like this entire pattern here. And the important feature of that electrical field is that everywhere on this line that bisects the two charges, everywhere on the vertical line bisecting the two charges, everywhere on that line is equidistant from the two charges, the negative one, which is not in our original problem, not a real charge, and the positive one, which in our original problem is a real charge. Everywhere on this line is equidistant from those two charges. So everywhere on this line has a positive electrical potential contributed from the charge on the right, a negative electrical potential contributed from the charge on the left. They're equal and opposite because they're equal size and equal distances away from the point on the vertical line. And so you can see immediately that everywhere on this line, the potential is zero. So this field, this potential of the electrical dipole exactly matches the boundary condition of our electrostatic problem. And so by the uniqueness theorem, oh, look, we just walked into a potential that fulfills our boundary conditions. And so we've walked into the unique single potential that solves the original problem of the charge in the electrostatic. So without any calculation, just wrote down what the potential is in some region of space over here to the right-hand side based on the potential of two equal and opposite charges located at distance A and to the left and to the right of the conducting sheet. It's just this potential. So that all worked because of the uniqueness there. That if you can somehow guess what the solution to your problem is, and it matches your boundary conditions, then that guess is the solution to your problem because it's matching your boundary conditions. Okay, this is a sort of that was a classic example of solving electrostatic potential, finding a solution of Poisson's equation by method of images. This is another classic example of finding the solution for electrostatic potential. This one's by separation of variables, but it also involves making a guess about the problem. So in this example, this one, so we're now set from Poisson's equation to Laplace's equation. In the last case, we had an arrangement with charges. This arrangement, we don't have charges in the region of interest. This problem is basically pictured over here on the right-hand side. What we're imagining in this sort of classic problem is that we've got some region of space here between the red and the green line, red and blue lines that we're interested in. The vertical lines and the horizontal line at the bottom here are conducting surfaces, and we've arranged that with the potential on these conducting surfaces to be on the left and the right, they're grounded surfaces, so they're at 0 volt potential, and on the bottom here, they're at a non-zero potential of 45 volts. So obviously there's some sort of distribution of charge that is kind of outside the problem. It's lurking on the boundary conditions that fulfills this arrangement where we have grounded plates on the left and right, and we have a voltage plate on the horizontal here at the bottom. That gives rise to those charges that must be there to accomplish this arrangement of potential. will give rise to an electrostatic potential in this region and an electrical field in this region. You could imagine that if you've got a positive voltage on the bottom plate, there must be charges around on the bottom plate, which are sources of field lines. Here I've pictured a few general field lines coming out, and they must be terminating on the grounded plates on the left and right. There must be negative charges on the grounded plates. We don't know what that charge arrangement is. What's been specified is the arrangement of potential. But anyway, this is what we want to figure out. What is the potential? What is the field in this region? So this comes down to solving Laplace's equation. Here I just wrote it out explicitly in Cartesian coordinates for a two-dimensional problem in terms of x and y. And the usual starting point for solving Laplace's equation in this type of problem is one of separation of variables. The separation of variables is an approach to solving partial differential equations where partial differential equation, a differential equation that's dependent on more than one independent variable. That partial differential equation is dependent on two independent variables, x and y. So this separation of variables technique is a way of facing that problem. The partial differential equation is dependent on a couple, two or more variables, and breaking it up into separate ordinary differential equations so we can use our ordinary methods to solve. And the breaking up of a partial differential equation like this one into ordinary differential equations involves making some hypothesis or some guess about the nature of the solution. So we're going to make the hypothesis or the guess about the nature of the solution, that the solution to the potential in the region of interest can be written actually, it's a solution of two independent variables, and on two independent variables. We're going to imagine that it can be written as a product of one function that depends on one of those two variables times another function that depends on the other one of those two variables. And that's going to be our hypothesis. And you know, this could be true in general, or it could be false. So right now we are making a guess. We are making a hypothesis that this we're going to see if this works. This separation of the works. It's like in the method of images. We made a hypothesis that the conducting plate and the point charge on the right look like an old problem that we have met with a positive and negative charge separated by twice the distance between the plate and the charge. We made that guess. And then we tested whether the potential fit the boundary conditions. And that's what we're doing here. We're making a hypothesis, coming up with an idea. We're going to solve for the potential and check that it fits the boundary conditions. Okay. Well, I'm going to, I've got two slides here. I don't want to spend which have a lot of text on them, a lot of math on them, which are the separation of variables and the identification of the solution to this problem. I don't want to spend a lot of time on them. I just want to give us the flavor of how this method works analytically, because then we're going to turn to doing it numerically. So the first step, as I said, in solving this problem is to make this hypothesis. We're going to separate phi, a function of x and y, into two separate functions. One of x, I call that function uppercase x. One of y, I call that function uppercase y. So upstairs here, here's the Poisson equation in two dimensions. I've made that hypothesis. I substituted in the product x, y, two functions of x and y separately. You know, when I differentiate with respect to x, I can pull the function of y out front because it's independent of x. When I differentiate with respect to y, I can pull the function x out front because it's independent of through this and divide it by 5. Imagine now dividing by the multivariate function phi, which is the product of x and y. If I divide this by xy, you cancel out the y here. This first term will just depend on the function x. If I divide this second term by xy, or the x's will cancel out, this second term will just depend on y. So by dividing through by phi, or product xy, I get the result that a differential equation, first term, involving x, and is only a function of x, not of y, plus a partial differential equation, which is a function of y and only y, the sum of those two equals 0. The only way that that could be true for every x and every y is that this first term is just equal to some constant, no matter what the x value. This second term is equal to some constant, no matter what the x value. That's the only way that the sum of these two terms, which could add up to 0 for every x, y coordinate. And so that becomes the separation of variables. That first term is equal to some constant, and the second term is equal to negative that constant. And these are now our two partial differential equations. And these are very familiar differential equations, right? They're just stating that the second order differential of the function x is proportional to x itself. So the second order differential of the function y is proportional to the function y itself, and beta squared is a convenient separation constant for these two partial differential equations. The general solution to the two differential equations, ordinary differential equations, can be written in different forms, but I wrote them in this form here in terms of exponentials. You could write them in terms of sines and cosines. In general, they're complex solutions mathematically. Of course, physically, they would only be the real part of physical significance. But here's the general solution. So here's the general solution. And if you look at this general solution, it's a product of some function of x, that's the solution of the first ordinary differential equation, some function of y, that's the solution to the second differential equation. In the exponents here, you see the separation constant. So you see the betas in the exponents here. It's why we wrote beta squared as a separation constant, because we're differentiating twice. Then it's more convenient to write the separation constant, which comes out each time you differentiate, write it as beta squared. And then these, so that's one parameter in this equation. In the general solution, beta could be any value whatsoever. And then the other parameters are these four parameters, the A1, A2, B1, B2, the coefficients of these four terms. So this is a hypothesized solution to the problem by separation of variables. It's all built on the assumption or a guess that you can separate the variables. But if you can separate the variables, if that hypothesis is valid, then this is a general solution to the problem. Now look, this is a very general solution because there's 5 parameters in this solution. There's the A1, the A2, there's the B1, B2, and there's the beta. And at this moment in this general solution, those can take any values whatsoever. So it's like some sort of enormous family of solutions to an enormous variety of problems that just is a solution to this form, this original form of differential equation. What a lot of the work is in solving the problem of the two vertical grounded plates and the horizontal positive potential plate is to take that general solution and by applying the boundary conditions on the left-hand plate, the right-hand plate, the bottom plate, one by one, apply those boundary conditions, work your way to the explicit solution to the problem that you have. So I don't want us to worry about all the details of that. You're going to apply a boundary condition specified by there's no top plate. You could imagine the potential is going to go to zero, which will go very fast on the bottom plate. So that's a boundary condition we use. We've got the left-hand plate and the right-hand plate. Those two plates are grounded, so we can apply the boundary condition of the left-hand plate. We can apply the boundary condition of the right-hand plate. And then finally, we get to the bottom plate. That's at constant positive potential, we call it phi naught. There's another boundary condition, we can apply that. What's happening as you step by step apply the boundary condition? Well, step by step restricting this general solution from what were any values of beta, A1, A2, B1, B2. And you're restricting them and restricting them and restricting them as you apply the top, the left, right, bottom boundary condition until you've got just one solution left that is the single solution that matches your boundaries on this problem. And so that's what's worked through here. The top boundary condition enforces that beta, which could be complex, is just real. The left-hand boundary condition enforces the fact that A1 and A2 must be equal and opposite to one another. The right-hand boundary condition enforces the fact that beta actually is real, but it can't take any value. It can only take certain discrete values. And then finally, the last condition here determines the amplitude of these coefficients based on the bottom plate potential. And you end up with this solution here. So this solution here, I know there's a summation in it, but it's a single solution. It's just one solution that fits our boundary condition. And it's a solution, if I plot it, that is this solution here. The black lines are the contours of the electrostatic potential. The magenta lines are just the gradient of the potential, which is the electrical, negative gradient potential, that's the electrical field. You see that the contours flatten out at the bottom because the potential is constant on the bottom plane. The potential on the side walls is zero. So as you walk upwards here, you're actually walking down these contours of electrostatic potential from phi naught towards zero. So this is downhill heading towards zero. But of course, on the left-hand and right-hand plates, you're already at zero volt. So this is I don't know how to describe this. Right, stand here on the top of it, right at the front of the room. Imagine the room is this potential. So all across here, I'm on kind of level ground. I stay right on the bottom plate, but I would start to walk down the potential if I walk towards here, but I'd also start to walk down the potential if I walk off to the side. That's the side. The two walls on the left and right, there is zero potential. The back of the room is a zero potential. Everywhere is downhill from this place. Okay, so we want to solve this problem numerically. So I'm going to set up a similar problem. We'll solve it numerically. by a method that's called the relaxation method. Relaxation method is a general term for numerically solving partial differential equations. There's sort of different variants of relaxation methods. I'll mention that later. But it's a very, it's a sort of general approach to solving partial differential equations where you basically break up your space in which you want to find the solution to the partial differential equation into some sort of grid or some sort of mesh. We're going to solve the problem on this grid or on this mesh. So here's the problem, this version of the problem we're going to solve on the grid, on the mesh. I've got, again, a left-hand plate, a right-hand plate, and a bottom plate here. Left-hand plate is zero potential, right-hand plate is zero potential, bottom plate is at a fixed positive potential binary. So that's the same. In the analytical solution, the problem I solved was these left-hand and right-hand plates were infinitely tall. And we solved the potential infinitely far above the bottom plate. In the numerical solution, the left-hand plates and right-hand plates are going to be finite height, and we're going to solve the potential just in the region between those plates. Look, analytically, I can imagine that the region of interest goes infinite to infinity vertically. If I'm going to put this on a mesh or on a grid and evaluate the problem with the mesh and the grid numerically, I need it to be a finite, not infinite grid. So that's why I'm having a limited grid here, and I'm putting a fourth boundary condition up here that the potential is zero at the top of this grid. So this is shown to, you know, the infinitely tall left and right plates was convenient for analytically solving. It's a much harder problem to solve it, potentially harder problem to solve it analytically with finite walls on the left and right. The reverse is true in the numerical problem, right? It's much easier to solve it with the finite walls on the left and right, and it would take us infinitely long time to make the infinite grid to solve it with infinite walls on the left and right. Okay. So we divide the region of interest up into some sort of mesh, some sort of grid. And of course, you could imagine that here you're making a choice about the grid size. You could make it finer, maybe more precisely map out the electrostatic potential, or you could make it coarser and yes, you more quickly map out the electrostatic potential. So you're always going to be making a compromise between precision and speed. Fine grid, we could get high precision map of the electrostatic potential at big cost in time. Coarse grid, poorer precision map of the electrostatic potential, but fast in cost. So here's my grid, and I'm going to apply Laplace's equation in this discretized space rather than Laplace's equation in continuous space. So I'm basically going to turn the differential equation, Laplace's differential equation, into a difference equation, a Laplace difference equation. So that's what I've got to do. What's in Laplace's equation in our two dimensions? It's just second order differential of the potential phi with respect to each of the two variables, x and y. So it's just got to be added to turn it into a differential difference equation, right? The second order differential with respect to x and y as difference equations for the electrostatic potential. And so these two lines here are where I've rewritten the second order differential with respect to x of the potential, second order differential with respect to y of the potential as a difference equation. This is just based on Taylor expansion. What the second order differential is of x and y in a Taylor expansion of the function phi about some point. If you want to think about it sort of visually, qualitatively, the second order differential measures the curvature of function phi. Right? The first order differential is measuring the slope, and the second order differential is measuring the slope of the slope, which is the curvature of the function. If I wanted to find the curvature of the function phi by the value of phi at nearby points, this is how I would find it. I've got a point at the center here, phi xy, and then I got neighbors, a little bit displaced in the positive x direction and a little bit displaced in the negative x direction. This combination evaluates the curvature on a grid of the spacing A. This is from the Taylor expansion, the curvature of the potential. Likewise, here's the curvature of the potential in the independent variable y. Yeah, this one, you imagine being at some location xy in the potential. You take a little step in the positive and negative directions in y now, little steps by amount plus a and minus a. And this combination will measure the curvature of that potential in that direction. So these on the right-hand side are the difference equations, and on the left-hand side are the corresponding differential, second-order differential potential. So now all I've got to do is replace, turn the differential, Laplace's differential equation, Laplace's difference equation. I just got to replace the second-order differentials with these difference equations here. So I just plug them in the equation. Actually, just the sum of them equals 0. So that is Laplace's difference equation. Like the sum of these two different differentials was equal to 0 was Laplace's differential equation. If you do plug these into the Laplace's equation and equate things, you get this result here. So these first two terms are coming from the second order differential with respect to phi. Come out of that. The second two terms come from the second order differential with respect to y. They come out of that. And then these terms here, you see that each of these differentials contain phi at the location xy, that are coming out of these terms here. And you can see the numerics of it. So, how many phi xy's do I have on the right-hand side up here? I have 4 of them. Minus 4 units. So that's the minus 4 here. How many terms with x plus 1? Sorry, x plus a, I only have 1 of them. How many terms with x minus a? Only 1 of them. How many terms with y plus a and y minus a? Right? 1 of each of those. So this is how this equation falls out. The a squared's in the denominator because you're setting in the numerator because you're setting this equal to 0, just cancel out. So this is Laplace's equation as a difference equation. And the way that we're going to use it is slightly rewrite it. I'm going to separate phi xy, put it on the other side of the equal sign. I'm going to divide it by 4, because it is 4. I'm just going to say that phi xy, so the potential at some point, imagine 3 points here, it will tell us is the average of the potential at 4 neighboring points. The 2 points to the left and right we use to sample the curvature in the x direction, and the 2 points above and below that we use to sample the curvature in the y direction. And so this is Laplace's difference equation written in a form that says that the differential equation or the difference equation just says that the value of the potential at location xy on the grid is simply the weighted average of the values at the four nearest neighboring points on the grid, the ones above and below and the ones to the left and right. And that's less Laplace equation. Okay, so that's sort of a breakthrough point, which gives us a way, leads us to a way of solving for the potential at all the grid points in the region of interest. And so this slide takes that result for Laplace's equation as a difference equation, says how we're going to use this to solve for the potential in this entire region of space here inside the boundaries. This is how we're going to calculate all the phi's at each of the little mesh points in the section here in this region of space. So this is how it works. So we're going to have an array of size that corresponds to all the mesh points in this array, in this sketch here, this graphic here. The mesh points will be points both on the boundaries, so there'll be a mesh point here, and a mesh point down here, and inside the boundaries. So it's that size of array. It includes the boundaries within the array. So we're going to have an array of that size, and what we're going to do is, to begin with, we're going to fix the potentials that we know. So we're going to fix the potentials on the boundaries. So on the left wall, the right wall, the bottom wall, and the top wall, we can fix those values in the array. There's zeros on the left and top and right, and then there's phi naught, which is at B, maybe 1 volt, 2 volts, or 3 volts, whatever it is on the bottom surface. The values in the interior, well, that's what we want to solve. I don't know the values in the interior, so we're just going to guess. And not a great guess, but I'll just guess there's 0 everywhere. That'll be my starting point. So all these elements of the interior, we're just going to guess them to be 0. That's the second step here. And then what we're going to do, we're going to start walking through all the points on the grid. We're going to walk through every point on the grid, and trial 1 will be just to walk through every point on the grid. We can start right up here. Just walk along horizontally, and then the next row below it, and then the next row below it. So whatever scheme we like, we're walking through all the points on the grid. And if we're at a point that's a boundary condition location, so if we're on the left hand or right hand or top or bottom walls, if we're at that mesh point, we're not going to do it. We're not going to touch the potential. But if we're at a point that's not in the interior, that's not on the left, right, top, bottom walls, we're going to recalculate. We're going to recalculate the electrostatic potential at that point using this equation here. So if I was walking across the top boundary, I wouldn't have changed anything. So then as I start walking across the second row, when it gets to this point here, I'm going to recalculate the potential at this point. I'm going to make it the average of the 4 nearest neighbors, which are the wall above, the wall to the left, and then these 2 interior points. And then we go on to the next point, do the same thing. And then we go to the next point and do the same thing, and so forth and so forth. So we slowly kind of spread through the mesh, right? We're going to sort of spread along here towards the right, and then we're going to go to the next layer, spread along there. recalculating and recalculating the value of the potential, updating and updating the value of the potential until we get down to this bottom corner. So that's been an update based on one walk through the grid of the electrostatic potential. We'll then take a second trial. We'll walk through that whole grid again, recalculating the electrostatic potentials, except we won't recalculate them on the boundaries because they're going to be fixed. We'll recalculate them through the volume. You can imagine that each time you walk through, you're going to be updating the distribution of electrostatic potential. I think I can imagine that on the first trial, because of this averaging, the first trial walk through, the potentials on the boundaries start to leak in to the interior region. In particular, this one down here, right? Whenever you average in a point that's at potential phi naught, it's going to leak in to the region above. Once it's leaked into the region above, on the next trial through, well, what's going to happen? Well, it's going to leak into the region above that. And then on the next trial, leak into the region above that. And slowly, this potential will leak into, like some sort of fluid or whatever, leak into the region of space that's interior to the problem. And it'll leak in and leak in and leak in. But what happens over time is that the adjustments of the potential, as you do trial after trial and trial, as the system kind of relaxes into the true solution, the adjustments get smaller and smaller and smaller. And so we're going to go around this loop, multiple trials, keep updating the potentials, but we're going to we're going to monitor the changes in the electrostatic potential. And if the changes in the electrostatic potential start to get smaller than some tolerance that we've set. Once they get smaller than that tolerance, we say we've got the result, the answer to for the potential in the interior region to the precision of our tolerance. And so that's the basic idea. So, in a way, unlike the analytical solution, which I guess I would say involves a lot of thought, right? You've got to think out your separation of variables and do your separation of variables and come up with your general solution. Then you've got to do a lot of individual work on applying the boundary conditions to restrict the parameters in your general solution to find the specific solution to your problem. This is a simpler approach. We've got a very simple version of Laplace's equation, which simply says that the potential at a point is the average of the four nearest neighbors. And we're just going to repeatedly apply that trial after trial for point after point in our mesh. So a very simple method that's just applied an enormous number of times. Just a remark down here. So this is what's called a relaxation method. It's called a relaxation method because you're starting with your potential that's a guess, and kind of as the boundary conditions kind of move in to the region of interest, you kind of relax into the true solution. So you sort of gradually lie down on the sofa and get the true solution to the problem, whatever it is. So that's why it's called a relaxation method. We're going to relax into it. There are various styles of relaxation. Different ways of relaxing into the solution. The one that we're going to do is that we'll update the new potential in this region in a given trial based on just the values from the old. So, you start with a guess, you update the values. Then you've got your updated values after trial one. You just use those values for getting trial number two. And then you just use the trial two values for calculating the trial three values. You update it that way. So that only uses the old value from the prior trial. There's another way you can do it, which is as you're updating values and calculating new values, supposing you're starting up here in the top right corner, left corner, then you could actually be using those when they come up again for other points in the mesh. So you can do that. That's a second way of applying this relaxation method. And then there's also a third way of applying this relaxation method, where actually, when you recalculate the potential based on the average of the nearest neighbors, you don't go to exactly that potential. You actually kind of overstep it a bit because you're going in the direction, you're hypothesizing that you want to go further in that direction, so you overstep. So what I'm saying here is that this relaxation method has a whole literature on different ways to optimize the relaxation method for quickness, for stability, and there are various different algorithms for applying the relaxation method. We're just going to be applying one, the most simple, straightforward one. Okay, we better get on with it. Let's go to the code somewhere. Okay, so here's my code. The code's really rather simple and straightforward because the method is really rather simple and straightforward. The code is longer than it needs to be just because I put in not just a solution to the particular problem that I was discussing, but to many different variants of that solution. I want to make this bigger now. Okay. Well, we need arrays and we need this cell. This cell starts by defining some important parameters that we're going to use for solving the problem. We need a mesh. We need to take that continuous space and discretize it. So we're going to make a mesh, and I'm going to make a mesh that is equal sized in X and Y, equal spacing in X and Y. I'm going to make my mesh that corresponds to, actually, I made the array size correspond to, here's the mesh size, 25. But here's the size of the array. This is the array 5. It's going to hold all the potentials, store all the potentials. This is going to include the potentials that are on the boundaries and the potentials that are in the interior. And the indexing of this two-dimensional array is going to go from 0 to 25 in X and 0 to 25 in Y. So there's actually 26 in indices. So that's why we're at 25 here and +1 here. 5 will be kind of like the current value of the potential that I'm working with after the previous trial. 5' is going to be the new one that I want to calculate for the new trial. So that's why there's a 5 and a 5'. I said we have to stop. We have to stop after some point, and we think we've got a good enough result. Tolerance is going to be the parameter I'm going to use to say stop. If the potential's changing by less than the tolerance, I'm going to quit. I'm not going to do any more trials. So that's tolerance. Remember, we got grounded left and right. Grounded on top, we've got a finite potential on the bottom. That's 1 volt. Here I'm setting up the boundary conditions on the mesh for the results of the current trial, which is kind of the initialization. So 5 on the left-hand wall, right-hand wall, on the on the left-hand wall and right-hand wall, and on on the top is set equal to 0 and phi on the bottom is set equal to 3. These are the boundary conditions. Say that again. So in I literally had this problem that you're describing, and it always seems backwards to me. But this here is going to specify the way I set this up is this specifies row 0 is at so the 0th row, horizontal row, is at potential V. Yeah. Is that, am I answering your question or not answering?
The problem is that what the plot rotates.
Oh, yeah. Yeah, well, that's a, yeah, and I know how to unrotate it. I learned how to do this, but I didn't get it in there. But when I do IM show, I think it rotates it.
Yeah.
Yeah.
So the 0, a that is representing first row is all 0.
The first row is all these.
Okay.
Is all these. Right, so I'm imagining, right, I drew that mesh for you, and I'm imagining that bottom row is row 0, and that's going to be all these. And then the columns on the left and far left and right, they're going to all be zeros, and the top rows is zeros. So that's what I'm trying to set up here. There's a lot of other cases in here, but I'm not going to, I might show you a couple of them. I've got to take this out. I got carried away before class. Look, this is what I've set up. No, that's not. Here's the 1 volt bottom. Is left and right is 0 volts, top is 0 volts, and the interior, the gas is 0 volts. Okay, so here's the entire code for solving the problem, the Laplace's equation, numerically. It's all packed into these lines here. Delta is just a variable I've introduced to and initialized to track how much the potential is changing. It's actually going to track the maximum change for any one element of the mesh. I'm going to have a nested loop here to walk over the n plus 1 and the n plus 1 elements of my mesh, of my grid. So this is just walking through the entire grid. Inside that nested for them, there's really only one thing I'm going to do. The one thing I'm going to do is that if I happen to be on a boundary, I'm not going to do anything. I'm not going to change the potential. If I'm inside the interior, not on the boundary, then I'm going to update the potential based on the average for the 4 nearest neighbors. And so that's what this logic does here in the comment line. On this if statement, condition is just checking whether I'm on a boundary. Am I on the bottom, at the top, the left, or right of the grid? If I am, phi prime, the updated potential is going to be the same as the original phi, the outgoing potential. So that's not changing if I'm on the boundary, but if I'm not on the boundary, then I'm going to make phi prime the updated potential. I'm going to make it the average of the 4 nearest neighbors. Here's the neighbor above, here's the neighbor below, here's the neighbor to the right, here's the neighbor to the left, and just average them. That's all there is to it. Now, coming out of this if-else statement, I'm building up by sweeping through the grid, building up from the old potential to the new potential. After I've done that, I'm going to find what is the biggest change. So this is now outside the nested form. What's the biggest change of all the changes I made? And once I've got the biggest change of all the changes I've made, I'm going to rename phi prime as phi, because now it's going to become our old potential that I'm going to try and update. And I'm going to go through this loop, right? I'm going to go through this loop, not a fixed number of times. I'm going to go through this loop until delta, the amount of potential is changing at most, is changing. I'm going to go through it until it's less than the tolerance.
Is there some physical mean? Like, is there like a characteristic tolerance? Because I've noticed playing with this that it stops changing, the graph stops changing significantly under a certain tolerance.
Yeah, I don't know if the tolerance is really a user. It's about the tolerance. How well do you need to know the potential? Right. I think that's it. Look, if you're doing a certain size grid, you know, you've already got an approximation, right? Because you only know the potential of the grid points. So, you know, calculating the potential to part in a billion at the points on the grid probably doesn't make any sense. So, I picked 10 to the minus 4, but that was just, you know, a number out of like a rabbit out of a hat. Okay, so here's the result. This is the potential in the region of interest. And it has the characteristics that I think we saw in the analytical solution. This is 1 volt downhill. You're walking, if you walk vertically upwards from the center, you're walking down to 0 volts with the other plate. But also if you walk off to the left or you walk off to the right, you're also walking downhill because it's 0 volts on those plates to the left and right. And if you wanted the field, it would just be the gradient. You could measure the gradient of this potential and determine the field. Let me just show you. So this is rather easy to solve this one problem, but it's also very easy to solve many other problems. That's why I put these other examples here. This arrangement of potentials is called an electric dipole arrangement. Imagine you've made a square box, 4 metal sides. You've got 2 sides opposite one another, positive charges and positive potentials, left and right, and negative charges, negative potential. It's called an electric quadrupole, kind of generalization of electric dipole. And we can, if we rerun the code, we can do this same relaxation into the solution for that potential. And you find what you might expect, right? The positive plates at the top and the bottom are the top of hills. The negative plates on the left and right at the bottom of valleys. There's kind of this saddle point halfway in between in the middle. This is what an electrostatic quadrupole field looks like. So it was very easy to just change the initial conditions and rerun the calculation. So it's a very flexible method, this numerical solution. Got to show you that. Let's set all these out. I want to show you at least one now. Let's go back to the original example. But I'm going to add something to it. I'm adding an interior boundary condition in these 2 lines here. So this interior boundary condition says that at one particular cell, right in the middle of the arrangement, I'm going to set the potential to be 0. I'm going to put a grounded wire perpendicular to the rectangular arrangement, and it's going to be grounded, so the potential on that interior point is going to be 0. Now, that's set it up as part of the initial conditions. I've got to modify the code if I do that. because that's an interior boundary condition, I don't want, if we're at that particular location, if we're at the location, the XY coordinates of the wire, then I also don't want to change the potential. So I've got to put in this little statement here, else. But if I rerun this code, let me go back up here, rerun the code, here's the result. Here's the grounded wire, which has distorted the potential around it from what it was if the grounded wire wasn't there. So you can put interior boundary conditions as well as exterior boundary. You will find the solution, right? Remember that no matter how you find the solution, with a relaxation method and walking through a grid, if you found that it matches the boundary conditions, you have found a unique solution to the problem.